All right, let's take a look at combined gas laws. Particularly what we want to do is sort of look at a dynamic where we've got some changes that are occurring kind of almost in real time. All right? So I'm not even going to read the problem, and I already am going to start off by drawing something that represents my initial and my changed system, right? So here, the initial conditions, whatever they are, and the change conditions, whatever they are. So that means, as we've discussed before in previous lessons, that we know we're looking at the relationship between pressure, volume, and temperature. So both initially and what the new sort of result is, right? All right, let's read this problem. Let's see what we've got. So we've got an aerosol container that is stored at 20 degrees Celsius. Stop. It's being stored there at 20 degrees Celsius. That sounds like that information right there. Haven't even read much of the problem. I already have something checked off. Let's move to a new storage facility that has not temperature control, has no temperature control. All right, so let me go ahead and change this right here. Live for you. Has no temperature control. Has no temperature control system. Obviously, that means the temperature can fluctuate. In this case, as a result, the temperature in the storage area increases to 40 degrees Celsius. So that means that now things change to where they are 40 degrees Celsius. All right, we're just moving right along. If there is 750 milliliters of aerosol gas in the container, so the volume right here is 750 milliliters. That's how much aerosol is in this container, which has a total volume of 800 milliliters. Will the container be able to withstand the changes to the gases? Okay, so a couple things here. So we still have three variables without information in it. The last part is it tells you the container. It tells you that this entire container is 800 milliliters. So that means what that means is this, is that you've got gases that are all in this container, right? But right here you've got some space, because it's telling you the entire container is 850 milliliters. So that means that right here we have 50 milliliters of volume, 50 milliliters of space. And so in industry, depending on what you're working with, there could be more or less. This is just a problem with some numbers that are not difficult for us to work with. So there's always going to be a little bit of space in there for the most part. Like if those gases were to, say, be cooled down, then they would take up less space, right? We know that, but the temperature would decrease, right? So then those molecular motion of the molecules would decrease, and they would take up less volume of space, right? And conversely, the temperature increases, higher molecular motion, kinetic theory of matter. It's going to move outward further away as there's greater molecular action, right? And so we can already look at this and kind of assume, wait a minute, we're probably going to wind up with an answer that is greater than something we're starting with, right? So notice the problem says nothing about atmospheres, right? It says nothing about the pressure. So that means you have to infer here. So you infer that you're at sea level. You infer that we're just at the normal atmospheric pressure, and that normal atmospheric pressure is 1 atmosphere. Okay. 1 atmosphere. And so now we realize that what we're trying to figure out is what will be the new volume of space required for 750 milliliters of gas that's at 20 degrees Celsius. How much volume of space would it need if suddenly there was energy put into the system and that those molecules moved faster, expanded outward? How much space would they need at 40 degrees Celsius? That's what this problem is asking us. So we're basically solving. So if this is the initial condition, this is our final condition. So everything here is a 1, everything here is a 2. Okay. So when we're done, we will look at this value here, and then we'll ask ourselves, Is it greater, less than 800? If it's less than 800, then obviously the container will be able to withstand the changes in the gas, because those gases would push outward, right? Regardless, they're going to push out because we have an increase in temperature, right? So we already have looked at the relationship between pressure and temperature, right? And so with Gauss-Sachs law, right? So here we expect that we should get a final answer that is greater than 750 milliliters. The question is how much greater will it be? Let's figure that out. So we have already discussed that P1 V1 over, okay, the T1 would be equal to P2 V2 over T2. We already know this. We're solving for V2. So before we do anything else, we're going to want to isolate V2 out of this equation. Okay. This is standard to do this, to rearrange this. The first thing you should always do is, I highly advise you make yourself a diagram, and it really helps visualize that. You'll get to a point where you won't need that, but it always helps. And then you list out the variables you have. The next thing you should do, you start with the original form of whatever equation fits for the problem you're trying to work out. Figure out your missing variable. You rearrange the equation to isolate that missing variable. Then you just plug and chug, and you just do basic algebra. All right. So notice this kind of gives people a little bit of a fit right here. So we want V2 by itself. So obviously, we would multiply this side by T2. That goes away. And then multiply this side by T2. So now the new form of our equation that we have is P1 V1 times T2 equals P2 V2. Okay? P2 V2. Oh, sorry about that. I forgot this over here. We still got that T1 a little bit. So now that's the new form of the equation. We need to solve for V2, which means we have to divide both sides, right? We have to divide both sides. Wow. Oh, I meant to press the pin. We have to divide both sides. I meant to change the color while I'm doing this for you. There we go. You need to divide both sides by P2. Now we have V2 isolated. So we just need to divide this side by P2 as well, right? And so now V2 is all by itself. So that's V2 equals, we've got P1 V1 times T2 divided by P2 times T1, right? So we know that essentially that when we divide by P2, we're essentially multiplying by the reciprocal, so it's going to put the pressure on the bottom, right? Okay. Okay. Now we just plug and chug. So V2 is going to equal P1. So P1 is 1 and P2 is 1. So there's a couple things we can do here. If you think about it, since both of these are the same, we could already strike through that because they're both a value of 1. Now, if you want to, I can always put this in here to show you how the units cross out. And I'm going to do that actually in this problem to show you how the units will cross out and we'll be left with only the unit we're solving for. But if pressure stays the same, if it's staying constant, and now in the new form of the equation we have the same value on top and bottom, then they're automatically going to cancel out. So you should see that that can happen. I'm going to go ahead and continue doing the problem as if we did not strike through the pressure. Okay. So we know pressure is 1 atmosphere times the V1, the volume is 750 milliliters. Okay, so we know that that is 0.750 liters. Okay, so that is 0.750 liters. Okay, times the second temperature. The second temperature is 40. So remember, you have to always add 273. And we've talked about it in class and on another video that 0.15, it doesn't change the overall value of what we're working with that much. So for general purposes, we can just use 273, and we're basically going to get pretty much close to the same answer. So right, 273 plus 40. I don't know why I'm using a calculator for this, but I know a bunch of you like to do that. There's 313, right? All right. So that would give us 313 Kelvin, right? Over T1, right? So we have to add 273 to this, so that gives us 293, right? So that gives us 293, and we know that that is Kelvin. And then the pressure here, again, is 1 atmosphere. All right. So atmosphere over atmosphere crosses out. 1 over 1 crosses out. K over K, Kelvin over Kelvin crosses out. The only unit remaining is liters, which is good since we're solving for volume. Okay, it's just basic plug and chug at this point. So we have 0.75 times 313, right? Divided by, you should get 234.75. Check my math for me. Divided by 293. Now you should look at that and realize that, okay, we've got a number that's kind of close, so it should be a fairly high percentage, right? Press enter, and we get 0.801194 blah 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 blah, right? So we've got 0.801194. There's a bunch of other numbers. This you saw that we don't need that, and the only unit left is liters. Okay, so 750 milliliters, 3 significant digits. So let's go with 3. 1, 2, 3. So 0.801 liters. We initially were up here working with milliliters, so we need to convert this, and so we know that that's 801. Wow, that was a horrible. All right, so we're at approximately 801 milliliters. Sorry. So now we've got the problem solved. Mathematically, we have a number, but the question is asking us, will it be able to withstand the changes to the gases? And so this right here, this is an interesting problem. You have a container that can hold 800 milliliters of volume. There's already 750 in there. Under these new conditions, 4 degrees Celsius, it's a little bit over 100 degrees Fahrenheit. The gases need 801. They need another 1/1000th of a liter, or 1 milliliter of space. So the question is will the container be able to contain that without rupturing? So this is a situation where you go 801, so you think back to the concept of that whole plus or minus uncertainty, right? Remember how you've in previous classes used plus or minus, so you have a plus or minus value of a little bit more, a little bit less. So it could be that an 800 milliliter container can contain, say, 105 milliliters to 755 milliliters. I'm just kind of making this up. It would just depend on the materials that are used. So in a statement like this, a situation like this, we might say 801 milliliters of space is required for the changes of the condition for the gases, and depending on the integrity of the container, it may not be enough, and the container might burst or explode. Or it might not. It may be able to withstand that pressure for a certain period of time. It is a possibility. So that's about the best way we could answer this right here. Certainly if you work on problems and let's say our calculation came out to 825, you would probably give a straight answer of no, because you need 825 milliliters of space, and there's 25 milliliters of space unavailable, the container will probably burst. Here, 801, it's probably just enough to hold that in for a little while until you can get it to a cooler temperature. All right. So you should see conversely that if we had to go to, if we went from 20 degrees Celsius to say 30 degrees Celsius or 35 degrees Celsius, we can make a very strong inference here that, oh yeah, we have plenty of space, because 40 degrees looks like about the maximum temperature range. So more than likely on the container, you would see something that says store between, I'm just going to make this up, 20 degrees Celsius and 35 degrees Celsius, which would ensure that the highest temperature it would be stored at would still leave enough volume of space in the container so there wouldn't be too much outward pressure pushing on the integrity of the container itself. All right, so hope that helped. It's all, remember, list out what you've got, come up with the original, write down the original form of your equation, rearrange it to isolate the variable you're looking for, and then it's just basic plug and chug algebra at that point. You know, basic plug and chug math. All right, ensuring that your units are canceled out properly. Remember, you should only be left with the unit that you're solving for, and that's how you know you're doing the right thing. Hope this helped.